In this lesson, we're going to look at acids and bases. So if you recall, an acid is a compound that starts with hydrogen, so like hydrochloric acid or sulfuric acid, and bases are compounds that have hydroxide in them and they end in hydroxide. So sodium hydroxide and magnesium hydroxide are examples of those. Both of those are based on the ARRHENIUS definition of acids and bases, and that's the only definition we're going to look at in 3U. So in ARRHENIUS's theory, acids, when they're put in water, they ionize, so they split into the ions that they're made of, and they produce one or more hydrogen ions. So for example, the hydrochloric acid that we looked at would split into hydrogen and chlorine ions. A base, on the other hand, is a substance that in water would dissociate to form one or more hydroxide ions. So if we had sodium hydroxide, that is going to dissociate into sodium ions and hydroxide ions. So this is a visual showing just that. So if I have hydrochloric acid, then that splits into hydrogen and chlorine. And if I have sodium hydroxide, that splits into sodium ions and hydroxide ions. Now, the one note here is hydrogen is actually not going to be an ion on its own. What's going to happen is that hydrogen will combine with a molecule of water to create what's called a hydronium ion. Okay, recap of properties of acids, which we talked about last year. So acids taste sour. They will turn blue litmus paper red, and red litmus paper will stay red. When they ionize, or the ions or electrolytes that result are hydrogen and whatever else that acid was paired with. So in this case, bromine ions. They will neutralize bases. So this is one of our special cases of a double displacement reaction. So H and OH will pair to form water, and the metal and nonmetal will pair to form a salt. Acids will react with metals to produce hydrogen gas, so they are corrosive with metals, and they will react with carbonates to produce carbon dioxide. So bases, some common acids, so citric acid in citrus fruits, carbonic acid found in pop, acetic acid, which is in vinegar, and sulfuric acid is in car batteries. Properties of bases, so bases have a bitter taste and they have a slippery feel, so different soaps and cleaning things often feel slippery. And that's because they're bases. They will turn red litmus paper blue, and blue litmus paper will stay blue. The ions or electrolytes that are created when they dissociate in water are hydroxide, and then whatever else that base was paired with. So in this case, lithium ions. They neutralize acids, so same thing, we have the double displacement where H and OH will combine to form water, and the metal and nonmetal will combine to form a salt. Bases are also corrosive, but they are corrosive with proteins, and so they will react with proteins to break a protein down. Common bases that you can find in your house are sodium hydroxide, which is found in liquid plumber. Magnesium hydroxide is found in milk of magnesia. Sodium bicarbonate is baking soda, and ammonia is found in window cleaner. So how we measure whether something is an acid or a base, we use the pH scale, and we're going to learn more in depth about that in 4U. So the pH scale runs from 0 to 14 with 7 in the middle. So 7 means that something is neither an acid nor a base, so it's neutral. And then under 7, something is an acid. So we can see that in our stomach acid is an acid, and then lots of foods that we consume are also acidic. We do have some foods like eggs, which are a little bit basic because they are over 7, and then different cleaners and things which are a little bit further along that scale, closer to 14. So we have talked about using red or blue litmus paper and the changes that would occur there to show us if something is an acid or a base. You've probably also used pH paper, which will turn different colors, and on the cap or on the container, it tells you what pH measurement something would be based on the color that that paper turns. We also have universal indicator, which will give us for acids, neutral, and bases. So it will turn red in an acid, it will turn green in a neutral solution, and it would turn blue in a basic solution. So other than that, we have other indicators as well, but they only work in certain pH ranges. So they each have a certain color that they are to start with. And if something that they are added to is in the pH range that they work in, then they will undergo a color change. So for example, methyl violet, when it's added to something that has a pH between 0 and 1.6, it would turn from yellow, which it is to start with, to blue when it's added to the solution. Anything that is above 1.6 as a pH, then when it's added to the solution, it's just going to stay yellow. And you can see here we have a lot of different indicators. And we'll talk about titrations later, and then get more in depth into titrations in 4U, but that is where one of the places that we will use indicators. All right, last part, we're going to look at naming acids and bases. So bases are simple because with the ARRHENIUS definition, we are only looking at compounds that contain hydroxide. So it's just going to be the name of the metal and then hydroxide. So for example, if I have NaOH, that is going to be sodium hydroxide. So just the name of the metal and then the word hydroxide is how we name our bases. Naming acids, so here it depends what that H is paired with. So if hydrogen is paired with a monoatomic nonmetal, so monoatomic means a single type of atom, then it's going to get the name hydro and then the name of that nonmetal, ic acid. So if we think about hydrochloric acid, that is just hydrogen with chlorine. And if it's a halogen like chlorine is, we're going to drop the IN. So that's going to be hydrochloric acid. If we have something other than a halogen, so if I have hydrogen with sulfur, so that's a 1 plus, 2 minus, so H2S. And how would I name that? So it starts off with hydro and then the name of the nonmetal. So this doesn't have the -ine suffix, so I don't have to drop anything. So hydro and then sulfur, sulfur and then ic acid. So hydrosulfuric acid when I have hydrogen paired with sulfur. If, on the other hand, I am paired with a polyatomic ion, then the name is going to be based on that. So you'll notice that a lot of our polyatomic ions here end in 8, and all of the names we're going to look at are based on those polyatomics. And we are going to choose chlorate as our example that we work through. So right beside this table in your data tables, you have this table. And so this is based on oxyacids from oxy ions, and so chlorate was ClO3 1 minus for its valence, and so that was chlorate. So this is called an oxy ion. It means that it is an ion with oxygens attached to it. So this is the 8 here. So this is where chlorate would come in. So that comes from the table. And if chlorate pairs with hydrogen, that would make HClO3, and that is an acid. To name that, so we can see that, so this is our starting point, so we're going to call it 1, but it is the second thing here. And so for our oxyacid name, so this is our acid made from our oxygen ion, I'm going to go down to the second thing here. So anything that is an 8 becomes an ic acid. So I'm going to chop off the 8, and the word or suffix chlor is what would fill in any of these. So chlorate, when paired with hydrogen, is going to become chloric acid. So if, look here, the 8 becomes an ic acid. Oops. The perchlorate would become perchloric acid. Chlorite would become chlorous acid. And hypochlorite would become a hypochlorous acid. So in each of these, for starting with chlorate, chlor is what would fill in all of these. So I can have perchlorate, and I'll look at what that is in a moment, chlorate, chlorite, and hypochlorite. So chlorate is the only one that's found in that table. So we're going to look at, given that one, how do we find out each of the other ones? So once again, in these, it's literally just chop off the 8, and what comes before it is what would come into here. So the first thing in the chart pairs with the first thing for the oxyacid. Second thing, when it becomes an acid, that's its name. Third thing, that's what it's called when it becomes an acid. And the fourth one, that's what it becomes when it's called an acid. So a chlorate becomes chloric acid when that chlorate pairs with hydrogen. So we're going to go through each of these now. So how do I figure out what a perchlorate is, what a chloride is, and what a hypochlorite is? For the acids, it's just each of those ions paired with a hydrogen. So a perchlorate is just a chlorate that has one oxygen added to it. So instead of ClO3 minus, it's ClO4 minus. And the important thing is that the valence doesn't change for any of those ions. So once again, starting point, what we're given in the table is the 8. When I have one oxygen added to it, it becomes a per8. So this was chlorate, so we're taking that chlor, remember, so perchlorate means one more oxygen than chlorate. So hydrogen added to that to make an acid then would be ClO4. So still 1-to-1 valence, H plus ClO4 minus, so HClO4 is the acid when hydrogen and perchlorate are together, and so that is called perchloric acid. So remember that this pairs with that. So this is the name of the ion, perchlorate. It's over here. And when perchlorate is in a compound together with hydrogen, that makes an acid, and the name of that is perchloric acid. So what about if I go back to chlorate, so that's my starting point that I'm given in the table, and I remove one oxygen, that would become ClO2. Once again, valence stays the same. And then remember, I'm just taking that root or the suffix part of chlorate, the chlor, and that is called chlorite. So ClO2 minus is chlorite, so one less oxygen than the chlorate. When I pair that with hydrogen, then I get HClO2, so that's now an acid. So the pairing, so the oxyacid name for chlorite would be chlorous acid. And last one, if I remove 2 oxygens, then I would have ClO minus. And so removing 2 oxygens is down here. That's going to be called hypochlorite. And when a hypochlorite ion pairs with hydrogen to make an acid, I have HClO, and the name of that one is hypochlorous acid.